Oh, there we go. Hopefully it'll last. It doesn't. All right. So, hey, so this is the last unit. I told you quarter 4 was all about electromagnetism. We're going to do circuits. We're going to do current first, learn how current flows. Then we're going to do circuits, and then after spring break, we'll do magnetism. And that's probably where we're going to end, is with magnetism. It would be really great if we got to quantum, but if we don't, no big whoop. All right, so current, electricity. We talked about electrostatics, and electrostatics is what you get when charges don't move, when they get fixed in position and create a field. By the way, if you're not happy with your electrostatic score, you're welcome to retake the test sometime this week, up to Friday. Okay. So if that's if you're like, I didn't do so good, then you could just do that. Okay. So this is a very simple circuit diagram. Very simple circuit diagram. And there's some items that we need to talk about. Okay. First of all, this is a battery or electrochemical cell. It's basically a source of artificial potential difference. Okay? So, guys, actually, ladies, okay. Water will flow over a cliff when there is a potential for it to flow. So if there's a high point and a low point for the water to go, the water will flow over a cliff and create a waterfall, right? We can put things in that waterfall and harvest a little bit of the energy. Well, a battery or electrochemical cell is an artificial waterfall. It's a pump. It's a pump that forces water to move. And the pump pumps electrons or pumps current from the positive potential to the negative potential, or from the high potential to the low potential. Now, I talked about this last time, that electrons move, and what charge are electrons?
Negative.
Negative. Yes. But it is actually not the electrons that we map. We map the change in electric field, so we use something called conventional current. Conventional current is positive and flows in the opposite direction of electrons. Conventional current flows from the high potential to the low potential. You can basically think of the long bar is the high potential, it's positive, and electrons are attracted to the positive, so they flow from the negative to the positive, while the current, which is positive, is repelled from the positive, attracted to the negative, so it flows from the positive to the negative. Does that make sense what I just said? Yes. Okay. So conventional current is positive, repelled from the positive electrode, attracted to the negative electrode. Electrons are negative, repelled from the negative electrode, attracted to the positive electrode.
So in that resistor there, when it goes through the resistor, it's still going towards the negative, yeah? What does it do once it gets towards that positive again? Does it go the opposite way?
It completes the circuit and goes into the chemical or goes into whatever the source is.
So we only need to know what it does for like one loop.
Yeah.
Okay.
As far as what's actually going on inside the battery, that you can deal with that in your third year physical chemistry class.
Okay. And then you said electron flow. Well, I guess it says right there, but that's the opposite, going from, it would be low to high potential, right?
Yeah.
Okay.
Yep. Electron flows from the low to high potential, conventional current from the high to low potential. Okay. Does that make sense so far? Questions?
Can they not go at the same time?
They totally go at the same time.
Then why don't they like stop the current or like the flow?
I mean, why don't they cancel each other out?
Yeah.
Because it is, when we diagram a circuit like this, it is the actual change in electric field that's really happening. The diagram is just something for us to understand in baby steps. So baby steps are current goes this way, electrons go this way. In reality, it is the change in electric field that's really happening, but that's, again, you can deal with that your junior year in college. Question? No. Okay. So, a couple of other things. 2 types of circuits. 2 types of current flow. One type is useful to devices and is produced in chemistry, electrochemical cells, and that is DC circuit, or DC charge, or DC current. DC is produced in devices, and it's used in devices. The problem with DC is it doesn't like to go through wires all that well, so sending it over long distances is a problem. So to alleviate that, we take the DC and we turn it into AC. AC current is alternating, and it's basically, whereas DC has one positive and one negative, one positive and one negative, the alternating is positive, negative, positive, negative, positive, negative, positive, negative. It goes positive, negative, positive, negative, and it does it 60 times a second. The frequency of alternating current in the United States is 60 times positive, negative, positive, negative, positive, negative. Remember those little vibrators that we use that vibrate the string up and down? You plugged them in and it went boop. Well, all those things were is a simple solenoid which basically vibrates a piece of metal on a magnet, and it was vibrating at 100 times or 120 times a second, because every time that it went positive, negative, it went but up. And the reason it's 60 is because of the diode they have, or the 120 is because of the diode they have. They doubled to 60. Okay, and there's a bunch of formulas that we'll talk about in just a little bit. All right. Other questions so far? Yeah.
So with the little thing you're talking about, does 60 hertz have anything to do with that number 120 being double?
Yes. It is 120 because they put a simple diode in the solenoid. So it every time. So 60 hertz. Imagine a sine wave where it's up and then down. Okay. So this is the symbol for alternating current. That's the symbol for. You actually might see this on your plugs. When you find a plug that plugs into the wall, it'll have that symbol and it'll say input this, because what's coming out of the wall is 60 hertz AC. Well, what that thing does is it takes the absolute value and it says, all right, the negative is not useful to us, so we'll take the absolute value and make it that. So it has two bumps, two back and forth for every single cycle coming out of the wall. Does that make sense?
So does direct current look like that green line right there?
No, direct current looks like this. Positive going that way, negative going that way. And this is what your devices use. Your devices use direct current. The battery, the electricity coming out of your battery, your cell phone, direct current. Electricity coming out of a AA battery, direct current. Okay. So far, so good? Cool. We'll revisit this stuff. If you're not completely on board, we'll revisit a little bit. Okay. So let's talk about what current electricity is. Okay. Current electricity is simply the flow of charge. Sorry, it says review. I haven't actually talked about this. So current electricity is simply the flow of charge. Whereas we previously talked about electrostatics, where charges were held in place and those charges created an electric field that pretty much didn't change. With current electricity, the charges are moving. And again, like I said, just like water flows over a cliff when there is a potential difference from high to low, water will flow through, or charges will flow through a circuit when we create a potential difference. Sometimes that potential difference is chemical. A battery or an electrochemical cell is a chemical reaction where the reactants give up electrons and the products take them. And sometimes it's a pump. We can actually cause things to move. This is a pump called a generator. I put something on the end and it turns. We'll play with this later. This is also a generator. And this is a tiny solar cell. Light goes in, electricity comes out through a process called the Photoelectric Effect, which I really hope we can talk about in May. But we'll see. Okay, so any device that uses current creates resistance. Resistance slows the flow of charge in the circuit. Resistance slows the flow of charge in a circuit. So any device that uses electricity doesn't actually use the current, or doesn't actually use up the charges, it just slows them down. Just like if you put a paddle wheel in this waterfall, that will slow the water down, but it won't cause it to stop entirely. Does that idea make sense? So when electricity goes through a light bulb turns on, that causes the charges to slow down, dumping a little bit of their energy, but it doesn't cause them to stop entirely. Okay.
Another one.
Discovering all sorts of little goofy devices all over the place. Okay, and of course, a circuit must be closed for current to travel. Now, a closed circuit simply means a loop. You know what a closed loop is? It means whatever goes out comes back. Like, our water in the Las Vegas Valley is a closed loop. We take water out of Lake Mead, we poop in it, and we send it back to Lake Mead. Yeah, it's a closed loop. We're one of the few places that use a closed loop, just because we can. It takes a lot of energy to have a closed loop. In California, they take water out of Lake Mead, and they dump it in the Pacific Ocean.
Fun.
Yeah. Because they require too much energy of them to pump it back into Lake Mead. They take water out of Lake Tahoe, and they dump it in the Pacific Ocean. That's California. Yeah. You've been to Disneyland, right?
That's something I tried. Sure, it's called eyelashes.
I'd like a churro. $9 for a churro. Okay, and we can diagram circuits with symbols. We diagram circuits with symbols, and we will. We will diagram them. They're called schematics. We'll get to that next week. This week, we're just going to focus on how current works. Oh, wait. What were you writing? That last line's not important. And honestly,
I'm just writing closed circuit. That's it.
Okay, closed circuit. Done. Good. Okay, so voltage, current, and resistance. Now, we talked about voltage when we talked about electrostatics. Who can raise their hand and tell me in their own words, what is voltage?
Power.
Yeah.
It's a measure of electric flow.
Electricity.
Current flow.
It's a measure of electric something.
Electric current. Electricity.
Yes. So, Lane gave me the textbook definition. Voltage is a measure of electric potential difference. What is electric potential difference?
The chance that it has to do something.
I don't know.
Okay, I'll take it. Guys, Sophie?
Yeah.
So, voltage is electric potential difference. It is the opportunity for the charge to flow. If there is no voltage, if there is no electric potential difference, charge has no reason to flow. Just like if there is no potential difference for water, there is no reason for the water to flow. Okay? You need to have the cliff for the water to go over. You need to have the pump. So electric potential difference, or voltage, is the opportunity for the charge to flow. Now, sometimes that opportunity is a chemical reaction. Sometimes it is a pump, a device used to force charges along. In our water analogy, you think of potential difference or voltage as the pressure that forces the water through something. When you turn on your hose, there's pressure behind the hose because your plumbing is connected to something downtown, a big pump downtown that forces the water out of the hole, and eventually goes out of your hose, and you're like, watch my God. Now, if you want to measure pressure in a system, you put a gauge external to the system. Like, if you want to measure the pressure in your car tire or your bike tire, you put the pressure gauge on the side of the tire, right? Because that would be the pressure flowing out, and it goes, psh, blows a little air out, and you can measure it. Similarly, if you want to measure the voltage or the potential difference in a device, you look at what it is before the device and after the device. If I want to know how much voltage is running through that resistor, I look at the voltage before and the voltage after. If this is 12 and this is 4, then I say the potential difference through that resistor or across that resistor is 8. So far so good? So if this is 10 and this is 3, then there's a potential difference across that resistor of 7. Cool? Okay. So you look at the difference, the top and the bottom, before and the after. Whatever it is before and after, that is the potential difference. Current is the charge flow. Current is the charge flow. It literally is the coulomb per second. An ampere, 1 ampere, is the charge rate of 1 coulomb passing through a device in 1 second. I'll give you the formula, I think, on the next slide. I hope. Or I could just write it down. Why don't I just write it down? I equals Q over T. That's the formula for charge. So current is charge moving divided by time. 1 coulomb, so 1 coulomb traveling for 1 second is 1 ampere. Shortened to amps. And just so you know, 1 amp is a lot of current.
What?
Yes, 1 amp can easily kill you.
What?
The good news is your body has a lot of resistance. So it would be very hard to express 1 amp through your brain. But yeah, 1 amp through your brain and you're done. 1 amp through your heart, you're done. The good news is you have a lot of resistance. The skin's a decent insulator.
How much? Like charge? How much is that charge? How much?
Less than 1.
I'm sorry.
The good news is cell phone batteries release their energy very, very slowly. So if you touch the current on the connectors on a cell phone battery, you don't like shock yourself. I will show you something that will shock yourself though.
Why do you fold stuff? Like, if you have a large enough fold, it doesn't hurt you, but if you have like certain amps,
I will show you. The formula we use is E equals IR. That's not exactly the most accurate representation. It should actually be written as I equals V over Sophie. Do we have a problem? Okay. We just got the giggles? All right. So it should be written as current equals voltage over resistance. So if you have 50,000 volts, like from the Van de Graaff, but your body has 200,000 ohms of resistance, you're not going to get a lot of current out of that. Okay. So what comes out of the wall is 100 volts, or 110 volts. The good news is you have a lot of resistance, so if you stick a fork into the outlet, you're going to get a little shock, but you're not going to get a lot of shock. So you have a big, yeah.
So it's okay to stick a fork in the outlet.
Absolutely. Okay. So, and just like, guys, okay, is this what happens when I give you M&Ms?
You spike it.
Because that'll be the end of the M&Ms if I can't, I have to talk over you.
Yeah, we'll probably only have popcorn from now
Okay.
on.
Are we, yeah, just popcorn from now on. Right. Understood, but try to clamp it down for the next 20 minutes. Okay. Okay, so just like we wanted to know the flow rate of water, I actually have a flow rate sensor. It's a little propeller, like a boat propeller, and you stick it down in the water and it spins. The only way to determine the flow rate of water is to actually get into the river and stick the detector into the river. Similarly, the only way to detect flow rate in a circuit is to actually put a detector in the circuit. So ammeters are wired in the circuit. So all the current going through this resistor has to go through that ampere meter first. So a current meter is placed in what we call series. We'll talk about series and parallel in a little bit. Okay. So if you want to measure voltage, you look at what the voltage is above and below it. If you want to measure current, you look at what the current is inside the circuit. And again, resistance is anything that slows charge flow. The water that shoots out of the dam, if those turbines weren't there, they would shoot out a lot faster. So the water, basically you have all that water piled up behind the dam, water goes through the dam, through the turbines, it spins the turbines. That spinning turbine slows the water down. Okay? That creates resistance, we harvest energy from that resistance. Similarly, chargers are like cruising along, like boom, I'm moving near the speed of light, boom, boom. Then they hit a filament in a little bulb. They're like, oh, I have to go through the filament? It's like getting through the turnstile in a subway. Like I have to get around, gets me really slow. Yeah.
Like us filing out of the store?
Exactly, yes. If you all tried to get out the door as fast as possible, you would be current and the door would be a resistor. Okay, storing charge. Capacitors store charge. That's what they do. And I got a couple capacitors up here from a device that you might not be familiar with. This is the Polaroid Fun Shooter. This is the Fujifilm Quick Snap. This is the CBS disposable camera. This is the Kodak just power flash. Okay, you guys know what these are? Yeah, this is what they used to put on the tables at weddings, so you could take pictures of each other and then collect them and you develop them. Yeah, these are disposable cameras. There were tiny cameras that actually, they put pictures on film. And they were only about $6. And they had basically two parts. They had a shutter that opened and closed, but the part we're interested in is the capacitor that made the flash go. So I'm going to charge up the capacitor. These capacitors are powered by one AA battery. This is a AA battery. That's it. You don't shock yourself with a AA battery. It's only 1.5 volts. When I put it in the camera and we're all very, very quiet, you can hear something interesting. You hear that?
Yeah.
That is the capacitor charging up. That really high-pitched whine is the capacitor charging up. Now I got some options here. If I want, I can release the capacitor through the flash.
What was that?
That was a flash. That's a flash. Okay. So I released that power through the flash. It was a pretty good sized flash. I'm going to do the same thing again. Everybody be very quiet. I'm charging up the capacitor. Now, what capacitors do is, in our water analogy, they're buckets of water. They store up charge and you can release it all at once. Now I'm going to release the capacitor a little bit differently. See the smoke? Yeah. I touched that about an hour ago on accident when I was taking this camera apart so I could get to the capacitor and the circuit board. I actually touched it and I realized it was fully charged. Yeah, I can still feel it on my wrist. So you can play with this. Just if you touch it, make sure the person touching it actually knows that you're about to get shocked. It won't electrocute you, but it'll definitely give you a fun little burn on your finger. But this is how a capacitor works. Okay, this is how a capacitor works. You get two plates, two buckets, and you use a source of potential, in this case, a AA battery. And when you close the circuit, what happens is the electrons travel to the buckets. You have two buckets. One bucket is holding positive charge. One bucket is holding negative charge. And the two buckets don't like having all those charges. They want to get back together and neutralize. But you're keeping them apart. And if you give them the chance, they're going to zoom back together as fast as they can. It's like, imagine having a bunch of North Pole magnets and a bunch of South Pole magnets. You hold them apart. You're like, I'm holding them apart. And you let go, they're like, bam, slam into each other. And that's what's happening. You have two plates. This is before they're connected. There's equal numbers of positives and negatives. You connect a source of potential and the charges start moving till the positives line up on one side and the negatives line up on the other side. Now, the charges want to go back, but you've placed something in between called a dielectric. A dielectric is a really good insulator. And the better your dielectric is, the more charge you can build up. Gesundheit. Yes?
Is there a reason that there's still positives on like the one plate?
This is to remind you that the plate doesn't become entirely negative and entirely positive. So it's impossible to make a metal plate fully negative and fully positive. It's partially positive and partially negative. So of the 56 trillion negative charges and positive charges, there's an extra 1,000 on this side, extra 1,000 on this side. Yeah, so that's why. Because people are like, all the electrons have moved. Like, no, if all the electrons move, the material will fall apart. So all the electrons haven't moved, but there has been a separation. So we charge up our capacitor. This one's fully charged. And we can release the power through a device, like a flash, or we can charge it up and short circuit it. Release the power through the end of my screwdriver. Sorry, release the charge through the end of my screwdriver. Yeah. This is one where I haven't exposed the entire circuit board, just so you can see the general parts. Same thing, flash. Lane.
So when you like drop your phone